All right, so the next topic is going to be projectile motion. Recently, I was at a conference at University of North Carolina, Chapel Hill, and I asked Andrew to please demonstrate to us what a projectile motion looks like. If you pay attention, you notice that this is a three-dimensional motion. However, we're going to limit one of the motion and one of the direction, and we're going to observe what the motion looked like in 2D. So let's define projectile motion. So projectile motion is a motion of an object thrown or projected into the air, subject only to acceleration due to gravity. Now this was true for free fall, but for free fall, the object moving along the vertical direction only. Now we have objects that are moving along the X and the Y direction simultaneously. So what we do in those cases is first thing is to understand is the motion along the horizontal is independent of the motion along the vertical. Um, and the motion along the vertical is identical to free fall, and the motion along the horizontal is going to be the one with the constant velocity, because if you're just looking the influence of gravity, then the gravity only acts in the horizontal direction, not in only in the vertical direction, not in the horizontal direction. So in the horizontal direction, there's no acceleration. Now what I have on the bottom is the kinematics equations that are applied in the X and the Y direction. So okay, so this is in the X direction, which is the horizontal direction. And you see Y, so that means in the Y direction. Keep in mind, we are applying these in these two directions, so all the vectors has to come from those directions. So the first equation, final velocity, that has to be the final velocity in the Y direction. V initial, which is the initial velocity in the Y direction. A is the acceleration. Well, for projectile motion, this is going to be our acceleration due to gravity. Well, in the x direction for projectile motion, there's no acceleration, or in other words, a is equal to 0. So this term goes away because you have 0 times time, that any number multiplied by 0 is going to be 0. This goes away, and this goes away. And if you look at the first equation, that is just saying that final velocity in the x direction is equal to initial velocity in the x direction, which is something that we already know, because if there's no acceleration, then the velocity doesn't change. So this first equation is not very useful to us. Similarly, this last equation, which is the square terms are equal, that is not useful to us. It doesn't give us any new information. So the only equation from the x direction in projectile motion that is useful is going to be this second equation. Now keep in mind, again, we're looking at a special case in the 2D motion, which is the gravity is the only thing that is influencing the motion of the object. So in that case, these are going to be our four equations. In the x direction, we have one. In the y direction, since we have gravity, so we have all of those three. And one thing to keep in mind here is the acceleration is just going to be negative 9.81. That negative is important. So one thing that is going to be demonstrated on this slide is the motion along the horizontal is independent of the motion along the vertical. So we have taken two baseballs and we dropped one baseball, and whereas on the second baseball we launched it along the horizontal direction. So the first one is dropped. What is the initial velocity of the object that is dropped? That's a D, dropped. One object is dropped and the other one is launched vertically. Sorry, horizontally. That's a horizontal direction. So the one that is launched horizontally, you'll note that it doesn't have an initial velocity in the y direction. And so is the one that is dropped. That doesn't have an initial velocity in the y direction. And every time interval, we have taken kind of like snapshots that I've shown in the previous lecture. So let's say this is at t is equal to 1 second. This is at t is equal to 2 seconds. This is actually, let's make it a little bit better. So 0.1 seconds, 0.2 seconds, t is equal to 0.3 seconds, t is equal to 0.4 seconds, and so forth. So as we take these snapshots, the vertical motion, when we observe, as you see, they line up. The one that is launched horizontally is lined up with the one that is dropped. And that is not just the case at one time instance, that is the case for all of the time instances. So that is because their initial conditions in the y directions are the same. And you'll also note that in this diagram that is drawn on the right, you see those purple vectors that's supposed to represent the velocity in the y direction, and the green vectors are representing the velocity in the x direction. Well, if you drop an object, it is not going to be traveling in the horizontal direction. In order for an object to travel in the horizontal direction, you need to apply that horizontal initial velocity. Well, if we're just looking at how the gravity influences its motion, well, gravity doesn't act in the x direction, so the object is going to have the same velocity in the x direction. And that's what you have seen for the object that was launched horizontally. Okay, so you see these purple vectors, they have the same length, which corresponds to that they have the same velocities if they started out with the same initial conditions. So here's the motion is broken down again. You have an object that is launched with an angle other than 0 or 90 degrees, so it has some initial angle. And when you see this initial velocity vector, you got to break it down to x and y components. And what it is showing you is that the velocity in the x direction, if you look at these vectors that are pointing towards the horizontal, they are the same. They do not change because there is no acceleration. Acceleration is change in velocity. So if there is no acceleration, then there is not going to be any change in velocity. So in the x direction, you have the same velocity. In the y direction, which is the more interesting direction because you have something that is being changed. Well, if you see these blue vectors that are pointing vertically, what is happening to them is they are decreasing in length, and at the peak, that velocity vector is not there because we know from the previous chapter is in free fall, the velocity at the peak is equal to 0 in the y direction. Okay, so because free fall is usually referred to motion in the y direction. So, and then on its way down, you see these vectors that are pointing now in the downward in the y direction. There is a symmetry. If you look at the motion, the time it takes for this object to go up here is equal to the time it takes for it to come down. And when we look at these vectors, the length of these vectors, at same height, they're the same, except for, I'm talking about the length, not taking into account the direction. Yes, the direction does get flipped. So one of the things I've asked you in the previous discussion was to figure out how high can you throw the ball, right? And to do that, well, we said, okay, if you launch the ball at this height, at some height, and then you catch it at the same height, then the velocity is going to have the same magnitude, but the direction is going to be flipped. So my equation, which was v in the y direction, which was v final is equal to v initial plus a times t, right? V initial and v final are the same, except for v final is going to be negative. So this is going to be negative v final is equal to v initial plus a times t. So then if you solve for time, or let's say you're solving for final velocity. So if you do that, then you add, so hold on, this is v initial. So you subtract v initial to both sides. So you get negative 2vi. A is equal to negative 9.81 times t. And then we get that v initial was just negative, well, the negative goes away, 9.81 times t divided by 2. So that's where that equation is coming from. That is taking into account that you caught the ball at the same height. In that case, the velocities are, the magnitude of the velocities are the same. So in this slide, what is shown you is the in the x direction, what we have is only one equation, which we have already talked about. In the y direction, we have these equations. And now here we are taking into account that a is equal to, in the y direction, is negative g, where g is just a number. So a is, another way to write that is a is equal to negative 9.81 meters per second square. So this is what our equation ultimately ends up being. There are many ways of writing these equations. If you want to stick with the original format of these equations and then add in the values, that's fine. Because when you do that, those equations are your starting point, and they can be applied in any situation. Whereas these equations that I have circled here, they are specific to projectile motion and to say that there is no horizontal acceleration. There is another equation in the projectile motion that we use, which is called the range equation. This is the range equation. In this equation, vi, this is the 2D initial velocity vector. Theta is the initial angle. I'll talk about where can this be used. And g is just 9.81. Of course, g is not negative. Remember, g is not negative. G is just a number. Acceleration due to gravity is negative. Right, so this range equation, the word range tells us how far, or it's pretty much is delta x. So how far from the initial point that the object traveled in horizontally only. The condition for this equation is that the object starts and lands at the same height. So let's say if you kick the ball from the ground and it comes back to the ground, then you can use this range equation to figure out how far it traveled along the horizontal. Let's say if you kick the ball on the cliff, it starts from the ground and it lands on the cliff. Well, it didn't land at the same height as it started out, so we can't use that equation in those cases. It's a very simple, very easy way to calculate the range. And one thing you'll note about this equation is that it doesn't have time. So sometimes you don't know the time, and if you don't know the time and you don't know the initial velocity, then well, you need to know the initial velocity. Well, if you don't know the time, then you can use this equation. Whereas if you do know the time and you don't know the initial velocity, you will ideally want to use this equation on the top. Let's say if the object does not land in the same height, in that case, what would you do? Well, you can't use this range equation. Well, you gotta use delta x. You have to use the kinematics, the 4 kinematics equations to figure that out. Okay, so this is a projectile motion simulation that is available by PHET Simulation. So there's a lot of, when you open to the intro tab, there's a lot of variation you can do to this. You can adjust the height, you can adjust the launch speed, you can adjust the object that you want to be launched. Let's say I pick piano. You can select velocity vectors if you want to see the components. If you want to see the acceleration components, that is also listed here, and you can use that. So you can also adjust the angle of launch. So let's say if I want to launch at 25 degrees, I will observe what happens to the piano, and then I will increase the angle only, and I will observe, and you'll see that for a 45-degree angle, it has traveled the furthest distance. If you want to make some measurements, you can take this measuring tool. If you point it at the last point here, it tells you the time, it tells you the range, it tells you the height of that object at that point. So if you place it over here, for example, it tells you the time to that point, tells you the range, and it tells you the height of that object. Now note that at a 45-degree angle, it has traveled the furthest distance. Now let's say what happens if we continue to increase the angle. Is it going to go to a higher height at a 55-degree angle or not? So let's launch it. See, well, you should note that it doesn't. And then if I increase it to 65, I don't know if that's an anomaly or is that the trend we see. So you see there's a trend. We should note that there's a trend. It's at an 85-degree angle. And if I change it to 90 degrees, it's just going to go up and come down. Now, if you really want to study the component of the velocity and the components of the acceleration, I would recommend increasing the speed a little bit. So it is in air for the longer time period. And I will make it too slow. I will pause it, and then I'm going to launch, and then I'm just going to use this. And you see, make some observation about what is happening to the green vector that is pointing vertically, what is happening to the green vector that is pointing to the right, what is happening to the yellow vector. Right? All of these things, all of these questions will help you understand the projectile motion. So try this out. You can add air resistance and see what happens to the motion. Is there an does air resistance add up any velocity in the any acceleration in the x direction? So yeah, make those observations and get a better understanding of projectile motion. All right, let's start with this example problem. So the problem states that during a fireworks display, a shell is shot into the air with an initial speed of 70 meters per second at an angle of 75 degrees above the horizontal. The fuse is timed to ignite the shell just as it reaches its highest point above the ground. Calculate the height at which the shell explodes. So there are some explicit information that is given. There are some implicit information, which is a hidden information that you have to apply here. So the first thing you should do always is start with a diagram. Start with to get an understanding of what it looks like. So if I start this out, I will say I have a object that is launched at an angle of 75 degrees. So this angle here, respect to the horizontal, this is 75 degrees, and it is launched at an initial speed of 70 meters per second. You see, this is a 2D vector. Now, what we do in projectile motion is we break it down into x and y components of the initial velocity vector, and we go from there. But to give you an idea of what is happening here is this object is going to be launched at this angle, so it's going to go, and then right at the peak, it's going to explode. Fireworks. All right. Peak of its height. And once you have a diagram, then you set up your x and y axis, or your origin. Where are you going to be measuring your x and y positions from? The easiest place to put it is over here. So I would say this is where my x is equal to 0, and this is where y is equal to 0. So since this object was located at 0, 0, x of 0 and y of 0, that is going to be its initial positions. Another thing we note is that this object explodes at the highest point. And one thing that we know about the highest point is that is where the final velocity in the y direction is 0. So at this point, the final velocity in the y direction is 0 meters per second. Well, we don't know what the final velocity in the x direction is. So again, initial and finals are 2 points. Initial, this is its launch is going to be my initial point, and where it explodes, I'm going to consider that to be my final. The question is asking us to figure out, calculate the height at which it explodes. So it is asking us what is the final vertical position, y final. That is what we're trying to solve for. Okay, so remember in the x direction we only have one equation, which I have easiest way to write this is delta x is equal to v initial in the x direction multiplied by time. And then in the y direction we have the 3 equations. The first one is v final in the y direction is equal to v initial in the y direction plus acceleration in the y direction multiplied by time. Then delta y is equal to vi yt plus 1/2 at squared. Right. And then you have the third equation, which in the y direction, of course, v final in the y direction square. Just adding those here. Subscripts helps us understand, okay, what the vector that we're using are initial, are they final? Just this gives us a little bit more information. All right, so these are our tools. Now we are only interested in motion in the y direction because the question is asking us for the maximum height. So y final. So the x is not going to be useful here. All right. Now we don't know the time, and what we're looking for is pretty much delta y. So if we don't know time and we're looking for the position, then this is probably our most useful equation. So v final in the y direction, that is 0 meters per second, as you say there. It is stated over there. Well, what is v initial in the y direction? Well, we're going to get v initial in the y direction by breaking down our initial velocity into x and y components. So the vector is something like this, and this angle here is 75 degrees. So if I calculate the horizontal, this is just going to be 70 times cosine of 75. This is going to be 70 times sine of 75. So my initial velocity in the y direction is just 70 times sine of 75. Okay, what does that come out to? And then I know initial velocity in the, final velocity in the y direction. I know the acceleration. I'm just trying to calculate delta y. And when you know delta y, you know y initial is 0. So you can plug everything in. So this is just 0 is equal to v initial in the y direction, which is 70 times sine of 75. That is going to be squared, plus 2 times negative 9.81 times delta y. So that's 70 sine of 75 squared divided by, which was negative 2 times 9.81. This is equal to y final minus y initial, because that's what delta y is. And since y initial is 0, that is just 0. So y final is just 70 sine of 75 squared divided by 19.6. Calculate what that comes out to. Okay. Yeah, should be around 233 meters. Now I have added that 233 meters to this slide because that's an information that we know. Okay, so same setup as the last one. Now part B is asking us to figure out the time to the explosion. So our initial setup is going to look the same. The only thing that we're trying to solve for is time. Now I'm just going to draw out the diagram here, and then we can go from there. All right, so if I want to find out what is the time, well, one of the equations that we can use is, which goes something like this: v final in the y direction is equal to v initial in the y direction plus a times t. So v final we know is 0 at the peak, and v initial was 67.6 meters per second. Acceleration is negative 9.81, and time is our unknown. So when you do this calculation, you should be able to figure that out. If you get time to be a negative number, then you know you did something wrong. So this is a pretty easy way of checking. So the value that I get about is 0.689, and I'm going to round that to 6.069 seconds. Let me see, what have I done wrong? Nope, that is incorrect. My number is incorrectly, so it's actually 6.9 seconds. Right, so part C of this question is now asking us to find the horizontal displacement at which the shell explodes. So what we need to figure out is x final. What is x final? Well, we know x initial, which is 0, and we know the initial velocity in the x direction, which was about 18.1 meters per second. If I recall it, that's just 70 multiplied by cosine of 75. Yep, about 18.1. And then we also knew the time, which was about 6.9 seconds. Okay, so in the x direction, we only really have one equation, so this just comes down to applying these knowns into that equation, which is delta x is equal to v initial in the x direction multiplied by time. So x final is our unknown, x initial is 0, initial velocity in the x direction is 18.1, and the time was 6.9 seconds. So 18.1 multiplied by 9.81, and that comes out to something is not right here. Yeah, this comes out to about 125 meters. There you go. So the last part is asking us to figure out the total displacement from the point of launch to the highest point. Now, if I were to draw out the displacement vector, which is a two-dimensional vector, and it is just going to look like this. The screen might not be a best option here. Let's use a dark blue. This is my delta R vector. All right, so R initial is equal to, well, the x component is 0, I hat plus 0, j hat. Now R final, well, in the x direction, that was about 125 meters, and in the y direction, it was about 233 meters. Include the units at the end. Now delta R is just going to be subtraction of the component, so my delta R is just 125 I hat plus 233 j hat. Now I need to represent this in terms of magnitude. Now this is fine. In terms of components, this is a vector R, this is a displacement vector. Now displacement, we need to figure out the magnitude of that. So that comes down to using Pythagorean's theorem. So 125 square plus 233 square, and then taking the square root of that. So delta R, the magnitude, comes out to about 264 meters. All right, so this slide is showing you what I was talking about with the range is at what angle do we get the maximum displacement in the x direction or the maximum range, and you'll see that is at the 45-degree angle. At the 15-degree angle and 75-degree angles, these are the horizontal range is the same. But as you see, the path that the object took for the 75-degree is different than the path for the 15 degrees. These two angles are called complementary angles where the range is the same. Although the range is the same, what about time? Do you think the time is going to be the same? Think about that. So in this example problem, I'll show you how we can use the range equation. Now it says we have a soccer ball which is kicked with an initial speed of 18 meters per second at an angle of 30 degrees above the horizontal. What is the range? So the range equation, let's write that down. Range is delta x, so that is v initial squared times sine of 2 theta. This is initial theta divided by 9.81, which is g. Okay, it starts and lands at the same height, so we can use the range equation here. And you'll see range equation is much simpler to use. So just plugging in the numbers, this is just 18 square times sine of 2 times 30 divided by 9.81. So the answer comes out to about 28.6 meters. Now, how would you do this problem without using the range equation? Well, you need to figure out the time. And to figure out the time, you could use the vertical direction, right? So if you know y initial and y final are the same, so that means delta y is equal to 0. You solve for time, and then from that time, you plug it into the delta x equation and solve for delta x.